Hi, everyone. Thank you for joining us today for the third of our four-part series in dynamic load understanding, the impact of structural loads on product development. Um, the Today's webinar is going to be Sculpting Success, Achieving Seamless Product Presentations with FEM and Simulation. So the presenters today are going to be me. I'm Tim Hunter. I'm president and founder of Wolfstar Technologies. I've got 35 plus years of experience, as you can see here on the slide. And then my co-presenter today is going to be Cindy Murphy. She's my director of engineering, and she's got a wealth of experience too. And we'd be real happy to talk to you about the ins and outs of simulation and what's going on today. So thank you, and sit tight. And I think we've got a nice presentation today, and we'll get right into it. So if you went to our webinar last time, you saw this V diagram we talked about quite a bit and talked about how it's cheap and fast on the front end and inexpensive and slow on the back end. And the whole idea is that we're trying to capture knowledge and bring that into the simulation environment, okay? And this is all part of our design build test cycle. And this is just what product development is. And today we're just going to focus on just this section here, just this section of system design, subsystem design, and component design. This is where the simulation happens. So we're going to focus on that portion today, okay? So getting into it here, the whole point of simulation FEA, it's an approximation. FEA isn't just an approximation. And so this is just a little definition I copied out of Wikipedia here. And it's just about breaking things into smaller, simpler parts, finite elements, discretization at a finite number of points. The method approximates the larger system, and the FEM then approximates and minimizes the error. Okay, it's just about approximation and minimizing error. Okay, FEA is an approximation. Okay, but on the upside of that is that all models are wrong, but some are useful. So this is a great little segment by George Bach. So I think this is great. So, and that's really what we're going to have with our simulation environment, right? All models are wrong, but some are useful, and some are very useful. So here we go. And today's presentation is going to be kind of FEA 101, okay? So this is about making sure that we're doing simulation and doing the right things on the very basic levels of simulation, okay? And the first approximation that we're making in doing simulation are something called shape functions. So shape functions are basically saying how is displacement or stiffness varying from one point to another, from one node to another. So typically there's a linear displacement, linear shape function, or there's parabolic shape functions where the displacement can vary parabolically from one point to the next. So for a linear shape function, you usually got two nodes on an edge, and for a parabolic shape function, you're going to have three nodes on an edge. So that's just typical FEA 101, what's going on. And going more into FEA 101, we're going to talk about all these different types of elements here. So we're going to go into the 0D, 1D, 2D, and 3D element types. We are not going to talk today about specialized elements like axisymmetric shells and solids. We're not going to talk about that, okay? We're just talking about the general elements today. So one more thing about basics here is finite elements is really about stiffness, right? So you've got a basic bar element here, right? So a bar element connecting node 1 to node 2, and its stiffness is going to be AE over L, right? Engineering 101. It's going to be the area of the cross-sectional area, the modulus elasticity divided by the length, the distance between the two nodes. So that's the stiffness. So basically, a force is equal to stiffness times the displacement of the nodes. And to generalize that formulation there for these two nodes, you could do something like this. Say forces at node 1 and node 2 is equal to the stiffness matrix divided by times the displacements, okay? So this is just a typical stiffness representation in matrix form for these 2 points in space, okay? Very elemental formulation for FEA. And then the whole idea is that you're going to put forces on your structure here, and you're going to solve for displacements, and you do that by inverting that stiffness matrix, right? So that's just for one element. If you had a more complex system like this, where you've got a bunch of elements hooked together in different ways, well, you would assemble these stiffnesses together in a matrix that would look like this, okay? This is just FEA 101. You have this global stiffness matrix, and the whole idea with FEA now is that we're going to be calculating displacements by inverting this stiffness matrix and multiplying it by the applied forces, okay? That's all FEA is just inverting a stiffness matrix, okay? It's a whole science of inverting big stiffness matrix. That's the basics of FEA right there, okay? So, taking a dive into the elements here, okay? The first most simplest element is a one-noded lump mass element, a 0D element. Okay, so this represents mass and inertia on the element. Okay, and typically you have to connect that into the structure via what's called an RBE, a rigid body element. So here I'm showing my lump mass being connected to my beam here via a rigid body element. Okay, and that's a very typical way of using a lump mass element, and they're great. They really are a way to simplify a large structure down to just its mass and inertia. Um, Now with RBEs, you've got two different flavors of RBEs, and so the kind of the Nastran terminology is RBE2 and RBE3. So an RBE2 is one where the central node here is the master, and it dictates the displacement of the remote nodes, which are called the slave nodes. So you've got the master node here and the slave nodes, okay? And and what's interesting with an RBE2 type formulation is because the mathematics going on is that the solver basically eliminates the remote nodes from the mathematical solution. So these remote nodes are basically being taken out of the stiffness matrix because it's all being dictated by this one point here through a transformation. Um, Whereas in our RBE3, the central node here is basically the slave, and it's being dictated by the average of the displacements of the remote nodes, the masters, okay? And then this is basically a least squares relationship between the remote nodes and the central node here. But this does not eliminate any nodes from the solution, okay? So you don't make your problem size smaller by using an RBE3, but you're not adding stiffness either. An RBE2 is adding stiffness, and RBE3 is not adding stiffness. So in the other solvers like Abacus, an RBE2 is called a kinematic coupling, and in Abacus, the RBE3 is called a distributed coupling, and in ANSYS, it's called rigid and or flexible. Okay. All right. 1D elements, springs, bars, and beams, they're a workhorse of conceptual modeling. They're extremely fast and accurate given the right problem. So if you just got some simple problems to solve that you kind of lay out by hand, these are really great elements. So you got a spring, which is going to be represented by stiffness, translational or rotational stiffnesses. You got the bar, like we kind of saw earlier, its properties are going to be area and modulus elasticity, and its degrees of freedom are translation only, no bending, okay? And their applications are typically trusses and connecting meshes together, maybe. And then the beam, it's got full degrees of freedom, all 6 degrees of freedom available. Its properties are the area, the moments of inertia, cross-sectional moments of inertia, and the modulus elasticity. And it's a very robust element used for looking at structures, connecting meshes, and looking at bolts. So these are all great robust elements and can be used in any way you want to. Just to, it's basically your modeling techniques that you want to use these things at. Okay. So getting into the continuum elements, the first ones are going to be the triangles. So you've got the linear 3-noded meshes, and you've got the parabolic 6-node meshes, and these are basically extremely stiff, and they're constant strain elements. Okay, these triangular elements are super stiff. Okay, do not use these. Okay, this mesh may be used for transition. Use with caution. Okay. Um, the parabolic 6-node element is great, okay? It can be used anywhere. It's a good representation of stress and displacement, and it's often used for coding solid tetrahedron elements. You got you got the quads here. They're linear 4-noded and parabolic 8-noded, and these representations are good for structural elements. Good represent stress and displacement, either the linear or the parabolic. Caution though that the aspect ratio of these need to be 4:1. Okay, so these are ideally a square, but you can stretch them out to be a 4:1 aspect ratio at max. And parabolic shells are often used to connect meshes to parabolic tets and things. Okay, caution with linear shells. Okay, big caution here is the degrees of freedom on the shells here are translation and then the 2 in-plane bending degrees of freedom. The out-of-plane rotational degree of freedom, the RZ, the drilling degree of freedom, That varies by solvers, and you have to look very carefully at how your solver is handling that drilling degree of freedom. Sometimes it's not there at all. Sometimes it's super stiff. You've got to just take a look at how that's being handled. Um, and then the other thing with thin shells are thin. So the edge of the element here needs to be 4 times greater than the thickness of the material, okay? So the mesh on the right, on the left, which looks pretty coarse, is actually a good mesh here. The mesh on the right is not, because the length of the element edge is about the same as the thickness of the element. This is basically modeling thick plates, okay? If you need a mesh this fine, you should go to solids, okay? This is really an important thing because a lot of times people will just push the mesh button and they'll make their mesh too fine for a thin shell element, okay? Another nice thing with 2D elements, sometimes some solvers have these membrane elements. A membrane element only has got translations, and you usually put these on the outside of solids and coat them with a very thin layer like paint, and then this gives you a very good representation of strain at the surface of the solid. Because a solid element gives you the subsurface strain, not the strain at the surface. So putting a thin coat of membranes on top allows you to get the strain at the surface, like a strain gauge. There's these wedge elements. These are similar issues to 2D linear triangles. The parabolic's got is good. It's got the good translational stress understandings here. In general, wedges aren't used much. They're mainly used for transitioning meshes. And then there's brick elements. Okay, brick elements perform well both linear and parabolics. Aspect ratio is important, so you need to make sure that you're a 4:1 aspect ratio, like for shells. But the thing is that the more distortion you've got, the more error you've got in bricks. And one of the things is that with bricks is that if you're modeling a plate or a bar, you need to have 3 layers of bricks through that to get the proper representation of bending. Okay, so you've got to model 3 thicknesses of brick elements through the thickness of a plate or bar. And because of that sensitivity to distortion and the need for 3 layers, I almost never use bricks. Okay, I know the old guys think bricks are the only way to go, but this is where I am at. Is that bricks, because you've got to have 3 layers through the thickness, I almost never use them. Okay, tetrahedrons. Okay, there's the linear and the parabolic. The 8 noted tetrahedrons, the linear ones, are overly stiff, bad for displacement, bad for strain. Never use them. They should just be outlawed, frankly. Okay. The parabolic tets are great. Okay. They're great for displacement and stress. They're highly insensitive distortion, and their single element through the thickness give good results. And these are the workhorse of FEA solvers. So these are great. Okay. A big caution here is that some of the meshers, one of the most popular meshers, I'm not going to mention the name of it, one of the most popular meshers, when you mesh tetrahedrons, it meshes only linear tetrahedrons. Then you have to go after the fact and convert those linear tetrahedrons into parabolics. I have gotten so many meshes from customers that are linear tetrahedrons that are I just have a heart attack when I get them. Okay, so be very, very careful with that. Okay. And then finally, we've got these type of elements called pyramids. These are pretty new elements. They're not used a whole lot anymore. Their main purpose is to transition from hex mesh to tetrahedron mesh. It's not supported by all solvers and the downstream application. So my advice is to avoid these if possible, but I have gotten meshes with these pyramids on them, and it looks nice. You know, on the outside it looks nice and square, but you have to be careful because a lot of applications don't work with them. Okay. General advice here, okay? General advice here is use 0 and 1D elements when possible. 2D mesh, use quads. 3D mesh, use tets. And 2D parabolic triangles to surface code a 3D mesh, okay? So that kind of wraps it up for my side of it here. And I'm going to switch it over to Cindy here, and she's going to take it over and tell us about more advanced applications of meshing.
Thanks, Tim. So there are several techniques to join parts or multiple parts for a system or a subsystem FEM. So what we're trying to do here is transfer stiffness from one part to another. I will cover bolt fastener modeling, and weld modeling in the next few slides. Bolts or fastener modelings can be simplified or more complex. Using multi-point connectors that leverage rigid or beam elements can be rigid, elastic, or inelastic connector behavior. The advantage here is you can request output from the connectors. So if you wanted to take a look at loads that are being applied to your fastener, your bolt, you can do so in your output. Rigid multi-point constraints, you can join multiple parts together. They're computationally cheaper than connectors and are less likely to overconstrain your model. The disadvantage is you cannot request output from these rigids. Good and sufficient parts need to be joined together in order to start your simulation. So many codes have an automatic fastener generator that includes preload in the bolt. And here you'll see you don't have to have a hole actually discretely meshed in your part. Attachment methods can be face-to-face, edge-to-edge, edge-to-face, and edge-to-edge. You can apply preload in the bolt generated from the torquing of the bolt in the assembly. So this technique allows you to change weighting methods at coupling nodes also. For preloading bolts, you can use rigid couplings or beams. So these are ideal for structural problems in which stresses in and around the bolt and bolt hole are not of interest to you. Merely you're just trying to connect those parts together and transfer stiffness. Preload is applied to the interior surface of the hole or the shank of the bolt. So you can apply preload there. And then you can also do that weighting method for weight distribution of the coupling nodes. Preload, while you can apply preload, it's not always required. A lot of models people do are not, we do not include preload in the bolts. It's just not an important part of the structural analysis. So 3D solid representation of the bolt with contact is probably the most sophisticated bolt modeling technique. All or most of the parts that are in the FEM that you're trying to fasten together, those have to be joined as one part in your main FEM. They're all the parts or most of the parts are modeled with 3D or tetrahedron elements for their mesh. Contact surfaces are defined for bolt to plate and plate to plate. And then for contact analysis, it's more of an advanced type analysis in which you want to do A to B comparisons between designs. Test correlation is going to be affected by friction among other variables for contact. If you've ever done a contact analysis, there's a lot of variables that go into that. So test correlation is very extremely difficult, but you can do it for A to B comparisons. Another part-to-part joint in a system or subsystem are welds, and these can be represented in your model in a few different ways. The anatomy of a weld is such that you have a plate. This is a fillet weld, a plate a horizontal plate, a vertical plate, and then the weld in between where you have two toes of the weld. The root of the weld is the diagonal dimension of the weld, and then the leg length, which is the weld size. First is simply kinematic constraints, which provide fully bonded connection between two nodes. These are kinematic constraints to join and align connections, which is an automatic method to set up a degree of freedom for the constraints. And then the area of influence for constraint nodes can be an engineering judgment or mimic the anatomy of the weld. For example, if the toe of the weld is, if the toe is a 1/4 inch, the area of influence for the constraint can also be a 1/4 inch, or the length of the weld is a 1/4 inch, your area of influence for the constraint can be a 1/4 inch. So this is a sufficient and computational inexpensive model that welds, particularly if there are many welds in your model. However, stresses in and around the weld will not be suitable for accurate results for those areas. Some more sophisticated modeling of welds includes shell elements. Welds are shells. Body of the welds are shells. Size of the shell can mimic the length of the weld. Before adding weld shells, the two parts must be combined into one assembly, even if there's no direct contact between the part. Part can also use 3D solid mesh with shell coat and use shell to solid elements for connection. Partitions are important with weld modeling. They can be made on the part that mimic the weld length, the weld leg length. This makes it easier to exclude or include elements during results review. So if you were to put a partition down on your plate, you could exclude that part because that is insufficient to look at for stress results in your final results. So one of the most sophisticated and detailed ways to model welds is with the 3D representation. Again, parts in the subsystem or system should be included into one cohesive model before the weld geometry is created. Again, even if there's no initial contact between parts. "3D solids are preferred, but if there are parts in the model with shells, shell to solid connections can be included. And this is the best way to get detailed stress contour results in the parts and the weld itself after analysis. And those results can be used for fatigue calculations in the parent material or one of the weld methods that are out there." To turn it back over to Tim.
Okay, thank you, Cindy. Here we go. So just to kind of wrap things up now, just kind of our final slide here. We got all these great modeling techniques we can do in FEA, and if we apply them properly and do the right things around picking the right meshes and doing the right things for modeling bolts and welds and things, we can end up being the hero so that we can come in and actually help drive this product development curve where we're able to get our learnings earlier and better early into the development cycle, so we can have early launches rather than late launches. So this is where we want to be, and I think with proper meshing tools and techniques, we can get there. Okay. So thank you all very much today. It was just a very short webinar today on this topic, and here's our contact information at the top. So please reach out to us if you'd like. Our website is on the bottom here, along with the QR code for it. And we really look forward to seeing you on our fourth and final webinar that will be on December 13th, and it's going to be on load-driven innovation, revolutionary product simulation and test. And we're going to pull this all together with a complete product development cycle, and hopefully you'll get to see all the types of things we've been talking about in this webinar series and how well it all flows together and what we can do with it. So thank you very much. I'm glad you made it this morning for this webinar, and we'll be sending out the recording to you all after the webinar today. And so we look forward to talking more with you. Thank you very much, guys. Bye-bye.